All right, it's time we come up with the definition of something called a derivative. We can graphically approach this by starting the conversation with a discussion of secants and their slopes, then moving to a discussion or an understanding of a slope of a tangent line, and from there we can step directly into what is a derivative. So let's say we had a curve and we're wanting to consider the slope of a secant line. Well, to find the slope of a secant line, or for us right now to find a slope at all, we need two ordered pairs. Right? Our definition of slope is dependent upon two ordered pairs. So I'll have an x value a here, and over here a y value f of a, and then a second arbitrary x value over here, which I'm just going to call x, and a value up here, f of x. Now, as we are aware, a secant line is a line that hits the curve in two places. So this particular secant line would look something like that. And to find slope, we need to find our pre-existing definition. We need to find a rise and a run. Our horizontal distance here, again, is commonly called run, and the distance traveled here would be an x minus a. And the rise, which is the vertical distance here, would be an f of x minus an f of a, which again is just another way of referring to our y values. So the slope of that line would be f of x minus f of a over x minus a. And this is sticking to the same rise over run thought process that we've used all along. Again, that would be a secant line. Now, a tangent line is a slope of a line is a line that hits the curve at one point only. Therefore, that line takes on not the slope of the curve between 2 points, but the slope of the curve at a solitary point. So how would we do that? Well, as you've done in previous exercises, you would take your x values here. We want to know the slope of the tangent line at A. What we would do is take these x values and move them just a little bit closer, just a little bit closer, and just a little bit closer each time. And that way, the slope between these 2 points would start to approach the slope at the 1 point that we're interested in. In other words, the slope formula that we have here above is a slope formula for 2 points, which is a secant. All right, what we want is the slope at 1 point only. Therefore, our slope is going to start off as it did before, but again, it's what you see physically happening here is the x values that you use are approaching the a value, which is the point at which you want to actually calculate the slope. And what you're seeing taking place here is a limiting process. In other words, the limit as x approaches a of this quotient is the slope of the tangent line, which is the slope of the curve at a single point. Now, this is one version of what you can use for a slope formula. What is more commonly used, there's another nomenclature that's used, or different symbolism that's used. Again, if this is your point A, and up here you have f of a, then what we will do is, instead of looking at arbitrary x values out here, what we will look at is, again, not an x value, but a distance. We'll call that distance h. So you are at A and you move a distance h, you would then be located at a plus h. And your function value would be f of a plus h. And our slope then would become the limit, and it's the same quotient, but it's going to look different. It's going to be an f of a plus h minus an f of a, but you note that when you subtract these two, since I established the distance as being in h, the denominator needs not end up being anything more complicated than h, and what we will do is we'll let h approach 0. In other words, we're going to let the distance between these two, right, distance here, go to 0. And again, that's what we will define as the slope of our tangent line, which is the slope of the function at a particular point. Now, what is this good for besides drawing a line that touches the curve in one place and one place only? Well, if you had a graph that illustrated on your x-axis illustrated time, and on your y-axis they're going to use the letter S quite commonly to denote position. Well, if we were to look at a value, which an A value would be a moment in time, where the F of A is your position at that moment of time, and run time forward some short distance h, again putting you at a plus h, and over here putting you at f of a plus h. What do you have when you find this slope? Well, the average slope, it would be, again, with the vertical change being on top, would be change in position. The horizontal change would be change in time. Well, change in position is also known as displacement. Over change in time. In other words, what we're looking at is how much you've moved over a certain period of time. And if you're doing that for 2 points, then what you're looking at is your average velocity, right? But if you take the limit, as h approaches 0 of this f of a plus h minus f of a over h, what you're looking at is not velocity over some increment of time. You're looking at velocity at some instant in time. What you have from there is not an average velocity, but the velocity, the instantaneous velocity. So if you want to know how fast you're moving over an interval of time, you can use the old version of slope. If you want to know what's velocity at some instant in time, then you have to use our slope of the tangent line to be able to find such a thing. This instantaneous rate of change is so important that it has its own name and it has its own notation, and it actually has multiple notations as a matter of fact. So here's what we have. We have f prime, again, that may look like a first power, but it's, if you write it carefully, it's supposed to be a little, like a little hash mark sitting at an angle. And that is the notation for derivative of a function at a number a, and it is defined as the limit as h approaches 0, and again, I've written this several times now, it should start to be a little bit familiar to you, of f of a plus h minus f of a over h, right? And again, that is assuming the limit exists. As we all know, some limits can fail to exist, so therefore some functions can fail to have derivatives at certain points. Now, be aware that this can also be written, of course, as we've seen, as the limit as x approaches a of f of x minus f of a over x minus a. But I will tell you that this version of the definition gets used the most because it really is the easiest and the most straightforward to use. So when anything is changing, our example was a position change, but whenever something is changing, its instantaneous rate of change is expressed by that derivative, right? Again, the derivative is not just slope, it's instantaneous slope. It's not slope between 2 points, it's slope at 1 point. It is instantaneous, okay? Instantaneous rate of change for anything that is changing. All right, so if they were to ask you to find the slope of a function at a point, not between 2 points, but at 1 point, this is exactly how it would be done. All right, for example, if you had the function f of x equaling 3 over x, and you want to know what is the slope of that function at the point 3, 1, then here's what we will be finding. We will be finding the limit as h approaches 0 of f of a plus h minus f of a over h. That is going to be our f prime of 3, right? So the pieces that need to go into this, not a bad idea to get them sort of figured out in advance. So my a is equal to 3. The a is the x value. It symbolizes the x value of which you want to find this instantaneous rate of change, this slope of a tangent. So therefore, f of a will be equal to f of 3, which is 1. They've already told us that, but I can plug the 3 in here real easy and see that for myself. Okay. F of a plus h is an f of 3 plus h. And f of 3 plus h is 3 over 3 plus h. Again, just taking the 3 plus h and plugging in for x in the function notation. Therefore, this will be equal to the limit as h approaches 0 of f of a plus h, which is the 3 over the 3 plus h, minus the f of a, which is the 1, and it's all over in h. What I'm going to do is get a common denominator here. So the limit as h approaches 0, 3 over 3 plus h minus 3 plus h over 3 plus h. That's writing the 1 with the common denominator of 3 plus h, all over in h. This is the limit as h approaches 0. And this is going to be a 3 minus a 3 minus an h, when you distribute the minus sign through, over 3 plus h, all over h. This gives me limit as h approaches 0 of a negative h over a 3 plus h. And instead of saying over h, let's say divided by h, for example. put this h into a division notation, which is the limit. H approaches 0, negative h over 3 plus h times a 1 over h. Going to multiply by the reciprocal. Cancellation will occur here. It's the limit as h approaches 0 of a negative 1 over 3 plus h. Now all I have to do is plug in a 0 for h here, and I get negative 1/3. All that work just for negative 1/3? Yes. All that work just for a negative 1/3. That basically means that this function has a slope of negative 1/3 at that point. So if you wanted to go on, you found the slope. If you wanted to go on to find the equation of the tangent line, then y minus y1 would be a y minus 1 equaling m, which is negative 1/3, times an x minus x1, which is an x minus 3. Okay, there's the equation of your tangent line in point slope form. If you wanted slope intercept form, you would simply distribute, add the 1, and there it is in the other form. Okay, there it is in the other form, if that is what you desire. Okay, so point slope, slope intercept, depending on what's being asked for. Okay, but regardless, there is the slope, there is the point, and there's the equation of the tangent line to that curve at that point. All right, now some of these calculations can be a little bit long. One of the things in calculus is you learn how much algebra you don't know when you take calculus. And so that difference quotient formula can be a little bit challenging to apply. All right, let's look at another one. Let's look at f of x equaling the square root of 3x plus 1. Let's find f prime of a. This time we're going to do it without knowing what a is, just to show you you don't have to know what a is. All right, so f prime of a, here's what I need. I need to know what is f of a. Well, f of a would just be the square root of 3a plus 1. What's f of a plus h? Be the square root of 3 times a plus h plus 1. Okay, so putting this into the formula, f prime of a would be, it's going to be an f of a plus h, which is the square root of, and I'm going to go ahead and distribute, if you don't mind while I'm here, 3a plus 3h plus 1 minus f of a, which is the square root of 3a plus 1, all right, over the h, and oh, I didn't leave myself enough room to finish writing it. Prime of a is the limit as h approaches 0 of this expression. Didn't leave myself room to write it. All right, what you will find with these, something that's going to be absolutely universally true. If you plug in the h right now, a 0 for that, you're going to get a 0 on top, you're going to get the 0 on the bottom. It's never going to work, ever going to work, just to plug in an h value of 0 immediately. You always are going to have to do some sort of algebraic manipulation. What we're going to do is multiply top and bottom by conjugate. We're going to multiply square root 3a plus 3h plus 1 plus the square root of 3a plus 1 on top. Multiply by square root of 3a plus 3h plus 1 plus square root of 3a plus 1 on the bottom as well. What you'll find with these, if you work enough of them, is that you don't really want to distribute on the bottom. You're going to be hoping that this h will cancel out at some point, so don't distribute. All right, multiplying first times first. Square roots cancel. So this is a limit. H approaches 0, a 3a plus a 3h plus a 1. Okay. What you're also going to find is that your outer and your inner are going to cancel each other out. So there's no need to write them down. Your outer products and your inner products here will cancel. So we're going to have a minus, and then last times last is going to give you a 3a plus 1. All over top of the h, as well as the square root of the 3a plus the 3h plus the 1 plus the square root of 3a plus 1. Now we're going to combine some like terms. Limit h approaches 0. 3a minus 3a will cancel. 1 minus 1 will cancel. What we're left with on top is a 3h. On the bottom we've got the h. Square root of the 3a plus the 3h plus the 1 plus the square root of the 3a plus the 1. Now here's the part that I was hoping to see happen. The h's will cancel. You really just about always want to see that happen at some point. So now I'm going to plug in my 0. So on top, since h is gone, when I plug in a 0, I just get a 3. Down here, when I plug in a 0, that term zeroes out. So I've got the square root of 3a plus the 1 plus the square root of 3a plus 1. So this becomes 3 over 1 and 1 make 2 square roots of 3a plus 1. All right, so there is f prime of a for that function. There's f prime of a for that particular function. And what this can be used for is to find instantaneous values, instantaneous rates of change. Okay?